This video serves as an introduction to a series of skill development activities focused on integrating spatial information into the design process. We're going to talk specifically in a minute about what types of layers of information we'll bring into the process, but I wanted to introduce you to the study area first. This is Happy Hollow Park in West Lafayette. Happy Hollow Park serves as an interesting study area for examining spatial data in the design process from a number of different perspectives. In addition to being a regional recreation amenity, Happy Hollow Park also serves as a lateral ravine running from the top of the bluff in West Lafayette all the way down into the Wabash River, meaning that from the entrance on Happy Hollow Road to the pedestrian trail entrance at the top of the park on Indian Trail, you climb nearly 200 vertical feet. Now, here in Indiana, 200 vertical feet, even over the course of a mile, is a relatively steep uphill climb. But in addition to that, what you're going to see popping out in the data here is a series of lateral ravines that also feed into Happy Hollow Park. Right? There is a significant amount of topography happening in this area. As we progress into this, we have to start thinking about what spatial data is out there and what's available to us. The types of information we can learn from really high quality topography data can help us understand critical slope information, the shape of and contours of the landscape. We can understand hill aspect, which especially at scale helps us understand the ecology of place, meaning that different species are found to be more dominant on different sides of the hill, for lack of a better description. Meaning that even within Happy Hollow Park, you're going to have different plant communities that are more significant depending on how much sun they get. So if you are on the east side of a hill versus the west side of a hill, the north side of a hill versus the south side of a hill, even within an area like Happy Hollow Park, we're going to be able to see these come out. How can we use spatial information available to us in GIS to understand that information? And finally, hydrology. Understanding how water moves across the site is one of the most critical parts of what we do as landscape architects. Our training prepares us to be involved in developing site grading plans, stormwater management and detention and retention basins. Happy Hollow Park is probably one of the most challenging places when it comes to dealing with erosion and stormwater management. You're going to get into that and see more in more detail what that really means as we progress through this video. Just real quick, I wanted to show you what we have here. The data that we're going to be working with is actually derived from LiDAR data. I'll explain what LiDAR is here in a minute. But what I will tell you is that having access to high quality topography information, contours, and the ability to have that in an environment like ArcGIS. There are other platforms for analyzing spatial information, but having it in this environment allows us to actually take advantage of many of our peer professions, civil engineering, hydrology, that have developed tools for quickly assessing the conditions of a landscape. And they've put those tools at our ready disposal if we know how to use GIS to capture that information. It wasn't that long ago that one of the best sources of information that was out there were paper USGS maps. Paper USGS maps served as the standard for a long time. The U.S. Geological Survey has been responsible for creating maps of topography across the United States. This information, you can see, was presented in a relatively standardized format wherever you are at in the country, and you can still find this information easily accessible even in the ArcGIS environment by adding it as a base map. Now, you should note that most of the buildings are just, black blobs. The road network is relatively well represented, but all you have here are 10-foot contours, right? And so the topography information is here, but it's relatively coarse in scale. In the early 2000s, a number of products started to show up that were digitizing the USGS maps and providing us with a cleaner version of those 10-foot contours that were being created by the USGS mapping process. And in some ways, these were a huge step forward. One of the challenges with this is that they were often developed by engineering firms who kept them as proprietary information, and so you had to pay to gain access. USGS has largely corrected this and makes their 10-foot contours available to us pretty much anywhere in the country, available for download through the Geospatial Data Gateway. However, 10-foot contours don't help landscape architects all that much. We tend to work with 1-foot contours or 2-foot contours, but 10 is still a bit really zoomed out for what we try and do when we're looking at site grading. So how do we move to a place where we can actually gain access to all of this information, right? A complete picture of the landscape. So this is LiDAR. And what is LiDAR? LiDAR is a series of technological advances that all come back to understanding that you're using ultraviolet light. So it's, pulses of ultraviolet light. Laser is the misconception often, but to do light detection and ranging. And if you'd like to learn all about LiDAR, I'd strongly encourage you to Google this NOAA publication. There's 200 pages of detailed information about how they collect and analyze this data. But the basics look like this. More or less, we started off by using airplanes to fly over the landscape back and forth, going ahead and using instrumentation that allowed us to capture the height of various objects, the height and density of various objects below us. So what does this really look like? So oftentimes we're looking to get transfer a site that we're working on and really start to understand the basic, features that are on that site, the buildings, the masses, the canopy or the tree canopy, how tall are the trees, the ground plane, all of these different surfaces. Well, with LiDAR, you can fly over it, creating a point cloud, and that point cloud allows us to start separating out the different densities of surfaces, and so you start to see the buildings start to separate out in the point cloud based on how long it took for light to reflect off those surfaces and make it back up to the airplane. What that really means is that they are, as they shoot a laser pulse to the ground, so this ultraviolet light to the ground, they are getting multiple returns per second for each one of those pulses that is returning back to the receiver and giving them indication of both the ground and the features that are above the ground and how dense those are. Creates this massive 3D point cloud of information. This can then be used to start separating things out and understanding what does the ground plane look like, what elements are part of buildings, what elements are part of tree canopy. And in this way, a LiDAR flyover can give us incredible information and a high level detail about current conditions on a site. This information has to be processed, and so it's not like we fly LiDAR and create a point cloud and magically all of the information is readily available to us. And so this is a pull from the NOAA handbook that looks at the different ways that things have to be classified. And so there is post-processing that has to occur, and there are specialists, geographers, civil engineers that specialize in taking those point clouds and turning them into additional available information. In some cases, that information is then made publicly available. In other cases, you have to purchase it. And the other, when it comes to looking for topography, which is what we're often after, the other thing that you should be aware of is that LiDAR comes back as a realistic representation of what's actually on the ground. And on the left-hand side here, you actually see that it looks, jagged and, it's imperfect, especially if you're looking at a 1-foot contour. And on the right, you can see that this has been edited and smoothed out to look more like what we'd expect from a clean topography line. The one on the left is actually more accurate. The one on the right is actually easier to work with. There are services and companies out there that will actually go ahead and take LiDAR and simplify it. And so, again, you have to understand that not all data is free, but at the, depending on scale, you can get amazing information about the landscape from these free and accessible data points that are out there. The other thing that you should understand is that the different ways that those data points can be represented, especially as we start looking at these complex 3D hillshades or the digital elevation models, DEM, digital elevation model, that stores topographic information in GIS. TINs, which is how landscape architects have often looked at any kind of digital modeling of the landscape is one way to look at it. It's more of a surface construction versus a grid, which this is really a flat, it's a flat TIFF file that has different values, so different colors that represent different heights within it. And those are broken up into small, small square shapes representing the landscape in that way. Both can be effective for helping us understand the landscape. You'll start to see as we pull some of this information into GIS, and I'm not going to spend too much time here, but I wanted to show you where this comes from, is that in order to gain access to LiDAR-based DEMs, or most LiDAR information, you have to understand that the file sizes on these can be enormous. This grid that you see here on the screen represents all of Tippecanoe County. Tippecanoe County is broken down into hundreds of these individual tiles. The three that you actually see here on the screen, right here, those three is actually the majority of Happy Hollow Park, right? And so in order to get this data out for Happy Hollow Park, to pull a digital elevation model for this, I had to use this grid, which it comes in as a shapefile. I had to go in and click my Identify tool, go in using a base map that I added underneath this, find Happy Hollow Park, identify which of these are out there, and then I had to go online, go to the data deposit, the repository. So in this case, the Indiana Map Atlas can point you to recently available LiDAR data for most counties in the state of Indiana. We also have a civil engineering professor here at Purdue who is actually contracted to produce the most recent update, the 2018 update to the LiDAR data set for the state of Indiana, and he makes all of that data freely available as part of that contracted work. So you can go pull all of that information, but you have to go in and download each one of these files individually. And so it can be a process to get there, but I didn't want to hide where this data is coming from instead of just dropping it in front of you. Where you go from that, from there is that once I've pulled in the four, those are the three squares that I showed you before, are these three. I actually went ahead and added the fourth, which isn't part of Happy Hollow Park, but it's adjacent to it. And I've taken these and put them together using a tool called Mosaic to New Raster. This is something that you can Google. It's a pretty simple process to walk through. Most things in GIS are out there and easily searchable to walk you through those steps. And that's where I'm going to go ahead and leave you here for now. When we resume, we'll start picking up with some of the first skill development activities.